Good afternoon, good evening, Doctor. This is Kawandatha from Group SWML26, and our project is about babesiosis disease detection in cattle. And as a brief introduction, babesiosis is one of the tick-borne diseases that affect the cattle, the animals. Uh, my name is Kawandatha, and that's my registration number. It's gentleman number, then the student number. So I will start with the content introduction. These are the things that are included in my slides. The introduction, the ResNet 18 architecture, efficient diesel architecture, how the model lines, how the model works, the optimizer, the results or the simulations, the learning rate, conclusions, and then the limitations faced during the model training, and then the acknowledgement. I'll start with the introduction. In this project for babesiosis disease detection animals, basically have a few classes of datasets that we managed to get. And one of them included the babesiosis positive images for the ones that are already affected by babesiosis, the plasmodium, which are negative images, but these ones they resemble their structure or their ring structure has or sometimes it is similar to babesiosis that causes confusion to the farmers or the vets, the veterinary doctors which increases the time for them to distinguish between whether the animal was affected by babesiosis or plasmodium. Then you also have the red blood cells, which are the negative or the healthy images, and then the leukocytes, which also are negative images. So in our project, I managed to implement two model architecture. I managed to implement two models using the model architectures or algorithms of ResNet 18 and then B0. EfficientNet B0. So I will start with ResNet 18 architecture. ResNet 18 is composed of 18 layers, which form the residue network. This is designed, the residue networks or the 18 layers are designed to solve the vanishing gradient problem. And vanishing gradient problem happens during backpropagation when the gradient becomes too small or too large, which may result or which may make the training of the model difficult, and sometimes it may stop the training of the model. The residue network in ResNet are composed of 4 layers, and each layer has different filters. We have layer 1, which consists of 2 blocks and then 64 filters. Layer 2, same blocks, but with 188 filters. Then block layer 3 with 2 blocks and then 256 filters. And then block 4 with 2 blocks and then also 512 filters. ResNet is composed of two basic features. We have the residue network or the escape connections. These ones are concerned with improving the convergence and the overall performance of the model while training it. Then you have the global average pooling, and this one is basically to performs the compression of the features. For example, the edges, the colors, and the sharpness of the image. Then you have the output layer, which consists of the fully connected layer. This one, this one takes the features extracted from the convolution layer and then determines, then maps them to the final classes. Remember, we have 4 classes: the Babesia class, the leukocyte, plasmodium, and then the red blood cells. So this is the lucid chart for ResNet 18. Basically, we have the first step or the initial step, which is the image input. We have our images that we have the microscopic images. Before entering them into the system or in the model, they are being shaped to a particular size, which is 224 by 224. And then they go under the 4 layers that I mentioned earlier. And in layer 1, which consists of the 64 filters, basically here on the image is passed through the first layer. this is what is going to happen. The model will learn the basic features of the original size of the image, such as the age, the colors, simple shapes within the cell. And then when the image is then passed to the second block, which consists of 128 filters. So here, uh, uh, under this under this block or the layer, uh, we shall be now focusing on the big patterns. For example, the group of pixels that might form the ring, because our our images will be in a microscopic format or microscopic images, which will be composed of the ring. So the stage two, or the layer two, for it to be focusing on those group of pixels or the layers or the rings that will be of those microscopic images. And then the third layer, which consists of the 256 filters, and this one will be concerned the abstract features or the combinations like the ring inside the cell, because you are taking the microscopic images of the cell, which will be concerned with those rings. And then the fourth layer, which was composed of 512 filters, and then two sprites. Basically, this one will be the actual model training, whereby our model will be responsible for thinking, is this a babesiosis infected cell, or it is a healthy cell, or healthy red blood cell. Then from there, we shall go to the global. We shall go to the global average pooling. Under global average pooling, here we shall be compressing the features, the edges. Then from there, we shall go to the fully connected layer. And this one takes the features extracted from the above convolution layers, and then it maps them with the classes that we have in our data sets, the babesiosis, leukocytes, and then the plasmodium. And then from there, we shall have our output, or the softmax. The softmax will be responsible for converting the, the values obtained from the fully connected layer into probabilities. For example, let us assume there is babesiosis, that will be maybe like 0.98. That means in that cell, we have a percentage of 96% of babesiosis. And we find the red blood cell has like 0.01, implying there is 10% of babesiosis in that particular cell. Then you shall go to the architecture of efficient net. Efficient net, we are focusing on specifically B0, and this is the initial one, the initial layer. It is good, it has a good performance. It is composed of parameters, composed roughly the 5.3 M. So efficient net basically uses compound scaling. Compound scaling helps in balancing the depth and the width of the width and the resolution of the image. So you have the key building blocks. Basically, you have the stem, the body, and then the header. The stem consists of the initial layer with a standard D convolution composed of 32 filters and the kernel size of 3 by 3, and then also two strides. And then the body consists of 7 stages, and each stage is made up of each stage is composed of a series of the MB conv blocks, which is the mobile inverted bottleneck convolution blocks. Under this, you have the squeezing, and then the scaling. Then you shall have the activation or the final stages. You have the global average pooling. This is for compressing, and the fully final connected layer, which is responsible for extracting the values from the convolution layer and then maps them to each class and the final classes. Then the softmax, for it to be converting those values into probabilities. And this is the ITSI Lucidity chart. Initially, we have our image input, we have our stem that composed of the filters. These are the 7 stages. Each stage is responsible for analyzing and determining how to learn how that cell is being or how that particular image cells are being arranged. The rings, then also to distinguish the final one, which has 1,280 filters, for which it performs the final role, whether to decide whether the cell has babesiosis or it is fully functional. It's a normal cell, a healthy one that composed of high red blood cells. So this is how our model lines. First of all, we have the initial step that comes first, the input data. The data that we input in consists of the blood cells of microscopic images. And these cells are from different classes, the babesiosis class, the leukocyte class, the plasmodium class, and then the red blood cell class. Then you have the data argumentation. Data argumentation is like filtering those images. For example, we have the random size crop. This one focuses on, for example, if the user uploads the image to be analyzed or by the model, the random size crop will pick a particular point on that particular image or the cell that has been uploaded. Then it will resize it and crop to a specific width of 224 by 224. Then the horizontal and then the vertical flip also come in the horizontal, the random horizontal, and then random flip. This will focus on determining the image, determining it whether these ones will ensure that the image can be read in all directions. For example, if the image was taken in a horizontal way, the model will be trained so that it can analyze it in a horizontal way. If it was in the vertical way, it can also analyze it in the vertical way, and then proceeds with the training or analyzing it further. Then you have the random rotation. Random rotation, our model will be trained to analyze the model in all directions. For example, it can be an angle of 30, an angle of 180, 360. So that's when a person takes an image in the microscope and then uploads this side, no matter the angle, our model will be able to analyze it in whatever direction the angle was taken, and then also give the feedback about the status of the cell. Then you have the color jitter. This one is concerned with auto-tuning of the color in the model. We train our model to understand or analyze all the different colors on how the model will be, or how the images may be uploaded. This will be determining, and this will be in charge of adjusting the brightness, the resolution, the black and white. Remember, these are microscopic images. They can be taken in different versions, either in the black and white format or the colored version. So our model has to be trained in all color sections so that it can determine the image, no matter the color has been used. Then you have the feature extraction. The feature extraction, after the data argumentation, we shall now go to the position where we shall select our model, which type of model to use. For example, in my case, I'm training my model using two model architectures, the ResNet 18 and then EfficientNet B0. Then you shall have the learning layers, the edge, the texture, and then the cell shapes, and then the parasite patterns, or the ring shapes. So then you shall go to predictions. Predictions are model output probabilities. Remember, probabilities are being displayed in the softmax layer. Softmax uses the values that have been obtained from the fully connected layer, and then it converts them into probabilities, which will be displayed for the prediction. Then you shall have the loss calculations. Under the loss calculations, we have the cross entropy loss. The cross entropy loss helps us to analyze how the model's prediction, how close the model prediction is to the correct output. If the entropy loss is low, this implies that our model has a higher range to our true value that we exactly expect or that we need. Then we have the class weighting balances. Then the optimization, we have the back propagation. The model optimization, we have the back propagation that computes the gradients. When I talk about back propagation, on algorithms used to train the model, this one helps us to update the weights so that this one helps us to update the models so that we can determine the prediction error, so that we get the error before the error that can be. This one helps us to determine the prediction errors to see how far our model is in learning. Then you have the model improvement. We can improve our model by making repeated epochs, training it. Remember, each epoch creates its accuracy. So the more we train our model, the more we train our model, using different epochs or the large number of epochs. This can help us to keep our model being updated and analyzing every image and every part of the image clear, so that it does not make any confusion or being used by other people. For example, like the vet doctors. By the time the vet doctors use it, our watch rate has to be high. For example, it has to be in 90s. Then we have the validation accuracy, which has to also be monitored. Since we have in my model, when I was training my model, I had the validation set, which consists of the images. So after training the model, the code was running to the validation set to start validating those particular images that were around in the validation set, and then after getting the beta accuracy, then the model is being saved in the models table on the models folder. So this is how our model works. First of all, you have the input. These are GameSmart stained blood smear images of size 224 by 224 pixels. Then the architecture that I'm currently using, it is ResNet 18, which is composed of 18 layers with the ResNet connections that help in deep learning without vanishing gradient. Then you have the efficient net B0, and this is the efficient net B0 uses the compound scaling, which helps us in balancing the depth, the width, and then the resolution of the images. Then it also uses the mobile inverted bottleneck convolution blocks, which is efficient and then also powerful. So these are the steps in the prediction process. First of all, we have the image input, whereby you're going to upload our image. You're going to upload our image that is going to be analyzed by our model. Then you have the convolution layer. Since each model has its own layers, and they also do the same functions, like extracting the image features, like the edges, shapes, and then the rings in the cell. Then you have the pooling layer, which comprises the spatial dimensions. And then you have the final fully connected layer, which makes predictions that are being got from the convolution layer, and then maps them with the final classes. Then you have the softmax, which converts the scores obtained from the the scores obtained from the final fully connected layer, and then converts them to probabilities so that they can easily be understood by the person who is running the model. For example, if Babesi had the composition of 0.92, and this will make 92% of Babesi. Then the output, this will be the class with the highest percentage with its confidence score. For example, the Babesi are being composed of 92.3%, and then the red blood cells being composed of 5.1%. And if someone sees such the scores, this will be a significant, and this will be like a confirmation that that particular cell is being affected by Babesia, since Babesia has a highest percentage in it. So these are some of the results images that were got after evaluating the model. First of all, you have the confusion matrix. The confusion matrix made the prediction. The confusion matrix was analyzing the test values or the test data set, and then also the predicted data set. So for Babesia, we had the test set was consisting of 118 images, and after testing our model, we came up with 113 images being composed of Babesia, implying that only 5 images were confused by our model, and that was giving us a good way to go, since our model managed to analyze most of the images. Then the leukocyte, there was no loss. All the images were analyzed well, and they were under the category of leukocyte. And then also the plasmodium, there was little confusion, whereby 2 of the images were confused with the red blood cells, implying that our model can now predict and differentiate between the cells, and then it can analyze and understand that this particular image or the cell is not a Babesia cell, it is a plasmodium cell. Then you have the red blood cells. The red blood cells, we had a total of 897 images, And out of those, 855 images were confirmed by the model that they were under the red blood cells, which was a good way to go since it was a good value to confirm our model. Then we have the precision recall, the F1 score for each data set. So we shall start with Babesia. According to our model, we have our recall value, which has a probability of around, because in this case it is around like 0.96, and this implies that 96% would be confirmed or was captured, confirming that this particular cell was composed of Babesia, which is a good figure to go with. And then the F1 score, which was around 0.78, which is also a good figure to go with. Then the plasmodium, and then the red blood cells. Sorry, the leukocyte and the red blood cells, these ones almost had the same range, since both of them were composed of the negative images, which were totally free out of Babesia. Then you have our pie chart. Our pie chart shows the class distribution in our test set. In our test set, we managed to confirm that 72% were red blood cells, which was a normal, implying that our model was fed with enough images to confirm that it is a normal, to confirm that it can analyze well and understand that the particular image or the particular cell is composed of normal cells, implying that it can easily distinguish a normal and unhealthy one. Then our plasmodium consists of 6.8, and then 11.1, which is for leukocyte, and then Babesia 9.5. Then you have our prediction confidence distribution by true class. So according to our class, we have the red blood cells being composed of the highest percentage in the range of 0.9 to 1, implying that our model can analyze well and understand, and our model can analyze well and understand a healthy cell. And then it can also have the next data set of the Babesia, which was consisting around 0.8, implying that our model can distinguish well Babesia unhealthy cell or unhealthy image without making any confusion with others. So this was for the first one was for the first images. The first two visualizations were for efficient net, and then the next ones were for efficient BNet 0. So we shall also start with the conversion matrix, which was basically considering the test set, and our Babesia images were 92 out of the 118. 92 of them were confirmed, implying the model is still learning, and I'm still building, and I'm still training it further so that it can analyze well and better using the efficient net BNet 0. According to our analysis, my efficient net B0, I was still learning somehow low, because according to the models I trained earlier, and the best model had naturally solved 90%, and yet ResNet 18 had 96.70. Blind for it was doing it in a better way than efficient net. That's why we are having some inconsistent values in efficient BNet, as shown in our visualizations. So this was the learning rate of our models. The learning rate scheduler, we are monitoring the bidirectional trace, and we set a restriction. If there was no improvement in the first three corresponding epochs, learning will be stopped, because there will be no change and we're just doing nothing. So it's better to stop the training of the model, since there is no change in the accuracy. Then you have the regulations technique, where the drop of 0.4, which randomly was 40% of the neurons, thus preventing overfitting. And the data augmentation, here we had the rotation, the flip, the color jitter, which was teaching the model robustness Then you have the weight decay in Adam W, which helps us to keep the weights small. That's smooth learning. And then the earlier stopping and better model saving. You are saving the model only when the validation accuracy improves. And then you are stopping at early stages in case there is no progress. That's avoiding overfitting. Then the results, the basic generalizing model is always kept and saved in the models folder. These were the conclusions and the limitations that I came up with. And I successfully built and evaluated two models from we managed to build two, since we had two model architectures, the ResNet 18 and the EfficientNet. Both of the models were trained from scratch. We didn't use any image. We didn't use any weight from the net images, the online 5 version. We didn't use any of that. We trained our models from scratch so that they learn from the first point. Then the models achieved the performance despite no pre-training. ResNet, the best actually that I got was 96% after 10 epochs. Then for efficient net B0, the highest validation accuracy was 90, and that came after 15 epochs. Then we also demonstrated effective handling of class imbalances using the class weighted loss. We proved the class core deep learning techniques work even without transfer learning. That's why we used it from scratch. Then the limitations since we are training our models from scratch, it could be a limitation somewhere. Then we also had limited data sets. For example, our target was to get like 1,000. Our target was to get like 300 or 500K images, but we only had 11K. Then we were using the CPU training, which was taking some good time, like 40 minutes to 30. So it was working well on my PC since it had a good RAM. There was no real-time interference. There's no real-time inference or mobile deployment tested yet, and this will come in the future time or the next days or the next time. We are going to build a web application in Python, and where we shall be able to upload these models that every person can just, whoever has a microscopic image, you just upload it and the validation takes place. The acknowledgement, I acknowledge our supervisor, Mr. Dr. Galiwang Marvin, for the guidance and support, the Makerere University courses for resource and environment, then the Mendy, this one provided us data set that we are using, which has so far worked well, training our models, and also the team members who have been collaborating and engaging and encouragement in this model training. Thank you, Doctor.